in ArgoDB und legt hiermit jetzt los.
Yeah, and now we switch to English.
Yeah.
Yeah, welcome. This is a story from, I think, last year. And probably the title doesn't tell you very much, libgcc when exceptions collide. I hope that at the end of the talk, you know what I mean by that. So that's actually a nice story. When I prepared this talk today, I had actually forgotten most of it, but it was nice to be remembered, although at the time it was not nice, because if you look at the topics we will be covering today, things like assembler debugging, finding endless loops, linked lists, which is, at least when I am involved, always a recipe for disaster, mutexes and concurrency, the Linux perf tools, C++ exceptions and their runtime support, libmusl, static linking, weak references in ELF, and probably some other stuff which I have forgotten here. To cut a longer story short, this took me most of a week, if not more, to get to the bottom of a really nasty problem. So what was that? For ArgoDB, we run our continuous integration in Jenkins. And we have a very simple rule. A pull request can only be merged if Jenkins is green. Well, obviously, sometimes we bend the rules, but in general, that's the rule. And I was working on something, I forgot what. It doesn't really matter because it's totally unrelated in a sense to what I was finding in the end. What happened is that I had mysterious shutdown problems. So in Jenkins, we run a lot of integration tests. And obviously, we start ArgoDB, we start ArgoDB clusters, we shut them down again. And obviously, the Jenkins framework expects that when we shut down the database, that processes go away. So this going away sometimes would just not happen. And since we are developing a distributed system, there's lots of processes, even for a single cluster. And we run many integration tests at times on the same machine, sometimes on different machines. So we essentially simulate the different processes on different machines on one machine, and therefore we produce a very high load on these machines. And if something doesn't shut down, then Jenkins at some stage obviously terminates the process and sends me a core file. And each of these core files of a database can easily be a few hundred megabytes. And since it's a cluster, it's multiple of those. And so I'm easily spammed with gigabytes of core files just because some silly process doesn't really shut down. There's one rather special thing we do, namely we want to have completely static binaries. And since if you have a network server and you want to really compile completely standalone static binaries, then you cannot use a glibc, because glibc has some of the network stuff implemented in loadable modules. Loadable modules do not work in static binaries in Linux. And so therefore, we need to do something else. And what we do is we build for all the continuous integration, or for all the releases, we build in a Docker container with Alpine Linux. And Alpine Linux is based on the C library libmusl. And therefore, we can build completely static binaries, which is a huge benefit because we can now, for every single Linux out there, regardless on distribution, regardless on version, we can ship the same binary. And every core dump we ever get can be analyzed on any Linux machine. And we just need the executable with the build and the symbols, and we can look at it. So that's good. So therefore, we won't want to give this up. But it's a special situation, and this will also play a role in this story. So I looked at one of these cores, and I found this. That's a core backtrace from a core dump. And we see that it was aborted. That means Jenkins has sent an abort signal from the outside. Well, at first you don't know. It could have been an abort because of some assertion failure, but in this case it was from the outside. And what we see is that not a lot is going on anymore. So there's only a single thread running. Usually ArangoDB has some 30, 40 threads. And main has already been terminated. So what we see here is some function which is called __ do global destructors auxiliary or whatever. We somehow see that it was compiled with GCC 8.3, and we are somewhere in the libgcc in some kind of unwind function. Unfortunately, if you just point your debugger at the core file, you can have your own source all you want. The debugger doesn't have the source of these, what is this libgcc? It's something which is shipped with GCC of this runtime library. It just doesn't have the source. So in the beginning, I was, I didn't know where to look and what's actually going on. I concluded somehow that it has to do with the global destructors of probably static objects. Is there any question? Oh, just an echo. And so all I had for now was assembler debugging. So with this core dump and switching to the assembler view, I was seeing that this is happening. Now, if you don't know any assembler, then just bear with me for a few minutes. You will get the gist of what's going on anyway, and we will switch back to C and then to C++ later. But if you do know, then you can actually understand in detail where it was stuck, because the RIP, the instruction pointer, was this lengthy address. That's how I found this code. And it plays around with the RBX register and stuff. And the RBX register had this value here. And looking at that address, I saw these 6 64-bit values. And now let's look what it does. So this here takes the RBX as a base and goes hex 28 and fetches the word into the accumulator. So that would fetch this word down here. And you already see that this is actually the same number. So the address here is the same as this field here. Then it fetches the same to RBX. It tests whether it's 0. If it was 0, then it would jump out here to this address. So that would move on, but it doesn't. Then it checks hexadecimal 18. So that would be that word here. Compares it with some other register. Well, needless to say, this didn't check out either. Or actually, it has no effect on the loop. And then it was checking the lowest byte of this word, that's the D9, which is, and then the 1 bit. That happens to be, okay, what is just not equal? I'm a bit confused. Text, test. In any case, it wasn't going out here either. And then it compared this with yet another register, and this was not equal, and so therefore it jumped back. So looking at the core, looking at the registers, I could see that something in this termination code was actually spinning in a tight loop without making any progress. Okay, if you go back to the backtrace, then we would see that we at least have a line number where things are happening and a function name. So finally, it was time to dig out the libgcc source code. So we went to the repository of GCC, or to some mirror of it, and looked in exactly this place here. Right, now if I click to this link, then my browser goes there, and we see we are back in C. Not yet C++, but we are back in C. So what's going on here? So this is the loop which is spinning. nice missing curly brace here. So it's just the if statement, which is executed all over the place. And it's already smelling like a linked list, because what it's doing, essentially, it's following the next pointer all the time, and then doing some conditions, comparing something, whatever. Obviously not going out here, like go to out, and just spinning. So this looks like a circular structure with the next thing. And obviously I need to find out what the scene objects is. We'll get to this. But for now, the structure it was looking at is this one. That's yet in another header file and took some time to find. But if you look at this here, what this does, 64-bit architecture, so we have one word with this pointer, one word with this pointer, one word with this. The union also has pointers all over the place, so therefore this is yet another pointer, makes it 4. Then there is a union, which has something in the bottom, well, somewhere a bit. That's another word. And here we have the next pointer, which is the 6th word. Great. So if you go back to the assembler code, that is your structure here. And the 6th word is obviously at offset 28 hex. That is the next pointer. So we indeed have an object which points to itself. One of these structures here has the next pointer pointing to itself. Going back to the code, this is the scene objects thing, whatever that is. At this time, I didn't know anything about the libgcc and the runtime of exceptions and blah. I didn't even know that it has to do with exceptions in the first place. But what I did know is that there is a circular structure of an object which points to itself. So we have some corruption in the data structures GCC builds up for us in the runtime. Bad. What did my poor old pull request have to do with that? I could only say nothing, because what was happening in my code didn't have anything to do. I wasn't even consciously throwing exceptions, but here you go. So if the data structure is ruined, then surely there must be a bug in libgcc. Admit it. You would basically immediately believe the same. So therefore, we must find places in this code here where this list of scene objects is touched. Now let's look at this C file here, and let's find for occurrences of this symbol here. It isn't too bad, because there's only 14 places. And let me go to the first one, to this one here. It says the unseen object. Is this large enough for everybody to see? Maybe this is better. The unseen objects list contains objects that have been registered but not yet categorized in any way. The scene objects list has had its PC begin and count fields initialized at minimum and is sorted by decreasing value of PC begin. Nice. Now, at the time, this didn't tell me anything. Probably this is the same for you now. In any case, I knew that this is a static structure in this module. So therefore, there is actually a chance to find all places which will ever modify this list. Obviously, there could be nasty C-like stuff where some pointer is copied elsewhere and then messed up. And it could be bad heap accesses or whatever. But fortunately, we could see what was actually happening. Now let's look through the file where things happening. This is the unseen objects list again. Another thing about the unseen objects, this is the place where we are. So here we actually only read the list. We just traverse the list, but it's already hosted in this way. This is something else. Here we seem to also following until we find a null pointer, but there's no modification at all. So that's not it. That's the unseen objects list. Unseen objects list. So the only place I could find which would ever modify this list is this place here. So I said, well, bug found. Something must be wrong with this modification here. So what is that after all? That is unbind find FTE, whatever FTE is. Unbind is probably something with exceptions or termination or whatever. To be honest, I already forgot what FTE is again, but never mind. Okay, let's just look at this here and see what it does. Here we have a struct object. That's the structure we were looking at, this one here, but a pointer. So P is a pointer to a pointer. No references in C, so therefore what we do is we point P to the address of the scene objects pointer. Scene objects is a struct object pointer. So that's the beginning of the list. We dereference the pointer that gives us the current pointer we are looking at. We follow the next and take the address again. So this is just the magic to follow to the next guy. And star P is the condition as to whether the pointer we are looking at is 0. That is some sorting condition. So we just sort by finding a right place by whatever, I don't care. And once we have traversed this singly linked list to the end, we do these two modifications. So the new object, which is supposed to be inserted, gets as its next pointer the pointer where we are. And the pointer where we are points to the next, to this guy here. So that's a straightforward insertion into a singly linked list. Nothing wrong with it, as far as I see. So therefore, I had actually proved that the only place which modifies this list doesn't have a bug. Yet, the problem was happening. So how can you catch a bug which you have just proved that it doesn't happen? I think this alone made me stuck for 1 or 2 days. Probably KW still remembers me moaning and asking myself and scratching my head. Now, the only way out was actually a practical one. I did see, and KW helped me with this, in the monitoring that indeed, when something was happening like this, that obviously after the fact, because I only could see it after the Jenkins run, that on this machine where something was running endlessly and not shutting down, one CPU core was actually spinning at 100%. That's what the monitoring of our machines in Jenkins actually told us. However, it was only happening in Jenkins, in a sense, batch processing. I couldn't actually look at it when it happens. And I had proof that it doesn't happen at all. So in this situation, actually the Linux perf tools came to the rescue. Fortunately, our continuous integration is set up such that we can also execute it outside of Jenkins. And we had identical machines at our disposal as they run in Jenkins. So I could actually repeatedly run exactly the same test scenario with the same code in the same type of Docker containers with the same compilation and everything on an extra machine, and could just hope that it would happen again. Now, but how can I catch it in the act? With these 3 lines here, actually, I can record whenever a process compiled here with this executable traverses this line in the C code. Let's look at what 1072 is. That is the only place I identified where this linked list is ever modified. And the Linux perf tools can do even better. They can give me a call graph whenever that point is traversed, and they can show the values of variables. So I said, if this happens ever again, I want to see for that run and I did know the process ID of the process which was not shutting down afterwards, whenever that would happen, I would like to see the call stack of any modification of this list, and I would like to see the local variable op and p. So that's exactly what is interesting here. And this basically doesn't cost any performance. So it was running unchanged because obviously every kind of modification would make the thing go away, as usual with difficult bugs. So the first one sets a probe, in case you don't know perf probe. The second one does a recording for certain events. And when you have recorded enough, you just hit Control C. And the third one transfers the script which came out into a human readable form. And now I could only wait. And I think it took another 24 hours or so until it finally happened again with my probe stuck into it. And indeed, it happened again. So surely I must now be able to decide why this list is modified and why this list is actually destroyed or made circular. And the thing is, I have also the stack trace, so I finally should know what of my code actually makes a difference such that this code is actually executed. Remember, at this stage, I didn't even know that it has anything to do with exceptions or whatever. And here is what came out. This is a slightly edited output of the perf tools after the scripting. So what do we see here? We always see the name of the thread. We give names to threads in Linux. We see the thread ID, that's this one. And we see another number of a thread. We see the time when it happens in some kind of seconds in something, and then microsecond accuracy. We see the probe. That's exactly my one probe I had. We see the values of these variables. That's words. And we see the call trace. So this guy is the last I have anything to do with. These two things here. Oh, it was something doing synchronized chart. It doesn't matter here. Anyway, this is something I have some kind of control over. But what I did see is that I was throwing an exception. Okay. Now, what happens if I throw an exception? Actually, I don't really know. But obviously, if I throw an exception, it somehow has to unwind the stack. And as I learned in this exercise, unwinding a stack isn't a particularly simple operation. And that is what these data structures in the runtime support are for. So that's still the executable name, but we are deep into the libgcc from somewhere here on. So it does want to raise an exception, and it, in the end, ends up in this unwind find registers FDE inlined, and the basic thing happens in unwind find FDE. Obviously, that's where I put the probe, and that's exactly this position here. Now we come to the interesting part. These two events were actually both happening in the same process. And look at the time difference. There is some 50 milliseconds time difference. So in a sense, these two exceptions were happening at the same time in different threads. So the other interesting thing is that the objects being inserted in this list here have identical addresses. So two threads were trying to insert something into a singly linked list at essentially the same time. And 50 milliseconds is obviously an eternity for a C++ program. But if you have a machine with 32 cores, hyperthreads, but very, very high load, then it's, and many, many threads. You know, every single Arango instance has something like 30 or 40 threads, and a cluster runs easily 6 processes, and we sometimes run 10 clusters at the same time. So we have literally hundreds of threads. And so it's entirely possible, even on a large multi-core machine, it's entirely possible that a thread is put aside and is scheduled out for 50 milliseconds. That's possible. Now, it seems that, first of all, two exceptions had to happen at the same time. And probably one of them had to be suspended whilst we are doing this. Obviously, inserting into a singly linked list cannot take all that long. In particular, it cannot take 50 milliseconds, but it could have been interrupted in the process. So obviously, the first thing you want to do is to see whether proper locking was in place. And indeed, here, there's a mutex, which is acquired here, and which is returned here. So that's a critical section. So it's utterly impossible that these two guys interfere with each other. However, the same object was inserted twice. If you look at the fine details here, this process essentially runs through the list of on-scene objects. And for each of them, it does something, namely search object, whatever that does. And then it inserts it into the list of scene objects. So in principle, it could have been that 2 exceptions trigger the insertion of the same object because both of them see this in the on-scene object list. And then they try to insert it in the same list. Now, let's just, for the sake of a thought experiment, I know it doesn't happen because there's the mutex, but even if it's happening one after another, if the same object is if we try to actually insert the same object into a linked list, then it can go wrong. How so? The first line is what happens in the beginning. We have, say, 3 objects, A, B, and C, and this is the next pointer visualized. Now what we do is we traverse along the list, go to the place where we want to insert, say B, and if a new object comes along, we take the next pointer of the new object, point it to the place where the next pointer of the old object here points to. That's the first operation. And then we simply put the next pointer of B to the new object. And we have a perfectly inserted new linked list. Now, if it so happens that you try to insert the same object again, then the only difference is that B is equal to B this time. So we are modifying the same struct. And the first thing we would do, we would put the next pointer of B to C to link it up here. But then, since it's the same object, we would now point the next pointer of B to itself. And we would find exactly what I found, a linked list which starts somewhere and ends up in an object which points to itself. Right, so this means this code is actually correct. However, it's only correct if the object we are inserting is not yet contained in this list. The very same object, the same pointer value. If it is, well, then it does this comparison until we find it, and then it makes a circular structure. Okay, so at least we have a trace why this happens and why this list must be host. But how could it ever happen? Because there is locking in place. So my eyes see a mutex, and yet it wasn't completely clear whether the mutex exists. So this line 1046 is this line here. So let's dig a bit deeper in this rabbit hole to see what this __ gthread mutex lock actually is. Well, for your convenience, I've put it here. And indeed, before it gets to its bloody work, it actually calls __ gthread _active p. Aha. So there is a possibility, at least, that the usage of this particular mutex, which I was clearly seeing in the code, is actually dependent on some runtime condition. So let's find out what __ gthread active p is. So that's now in a different file. So that here is the mutex I just showed. And here is this condition. And I think I have to go one further slide to show you what this __ gthread active p is. So that's a bit cryptic, but in the end, it points with some C magic, this particular pointer, __ gthread active pointer, to this address here, gthread active proxy. Now, don't think that looking this up is just a click in your IDE. This is very, very deeply nested if-defs in bloody preprocessor C code. So therefore, it took me quite a while to actually find which of the many __ gthread _active _p is actually used here. But I found out that on Linux, it's this one here. So if we are using glibc, it's doing this call and it's defined like that. If we are on some Android variant called Bionic, then we are doing this. And otherwise, which turned out to be the truth here, on libmusl, which intentionally doesn't fake to be glibc because it isn't, it's actually this guy here. So it's, this is, my slides are bad. Let's look at the code directly because here is an invisible space. So let me look at the code in the browser here. So just to give you an impression, this is the beginning of the case there that your platform supports weak references, but it's not BSD and it's not Sun and System 5 revision 4. No, it's all not all that. It's neither FreeBSD nor Solaris. And then I found this comment here. For a program to be multi-threaded, the only thing that is certainly must be using is pthread create. However, there may be other libraries that intercept pthread create with their own definitions to wrap pthreads functionally for some purpose. In those cases, pthread create being defined might not necessarily mean that libpthread is actually linked in. Okay. I have to say that my heart sank a bit when I read this. It seems that the authors of libgcc, in their infinite wisdom, tried to squeeze something out of this code by not acquiring a mutex when they come to the conclusion that your program is not multi-threaded. And that's indeed what's going on here. So here you can actually see the spaces. Needless to say, on libmusl, it does this guy here. So the question is, what is __ gthrw _ and what does it have to do with pthread cancel? Don't worry, we are getting to some kind of C++ very soon. Digging a bit deeper shows me that this is happening if we are in the supports weak case and gthreads use weak. Now, imagine that since I'm not a C compiler, I don't actually know whether this macro is defined or indeed non-zero. So therefore, reading this kind of code makes it next to impossible, or at least not easy, to decide which of these cases is actually happening. But in the end, it turned out that this piece of code here is actually happening. So the __ gthrw2 does something like this, which is defining a name to be a weak reference to another name. So what's a weak reference? And the other guy here, the one __ gthrw, essentially just puts a prefix before that. And if we go back to this other place here, what is __ gthrw_ cancel? This puts prefix before this cancel. So what this actually does, it essentially puts this pointer to point to an address which is given by a weak reference. So, you know, linking is black magic, probably of one of the worst kind ever. And what is a weak reference in the first place? And another thing I learned on this trip, if you put a weak reference into an ELF object file, it says, here's a symbol, and the linker will resolve this to either something else, if that something else is actually defined in the program, or to a null pointer otherwise. So, okay, here on the slide I've put that a weak reference to pthread create is used. That is what is happening on glibc, but bear with me. The idea obviously is, in a multi-threaded program, you probably link pthread create. So therefore, if you point a weak reference to pthread create and resolve that at link time and assign it at runtime to a pointer, then that will be non-null pointer if pthread create is linked into your program. And surely if you use a multi-threaded program on Linux, you almost certainly use pthread create. So far, so good. And the other thinking is, if you have a single-threaded program, then it probably doesn't link pthread create. And even if it does so, it doesn't really matter, because then you just have the optimization for single-threadedness not. Unfortunately, on libmusl, we are not using pthread create, but pthread cancel, which isn't a big deal if you are linking against a shared library for libpthread. Because if you link to the pthread library, then you can either link to it or not. If you link to it, you have both pthread create and pthread cancel. If you don't link to it, you don't have either of them. So that is the thinking behind this place here. And the argument here is, in a multi-threaded program, surely has to use pthread create. And they were just not thinking of the case that somebody could statically link the executable, use a C library, which is not glibc, in which the pthread cancel function is in a different module than the pthread create function. Well, as it so happens, in libmusl, every one of these pthread functions is in its own module. So therefore, the linker dutifully does not link the pthread cancel module in case you're not using it. Well, we are doing C++. And as far as I know, C++ in the standard doesn't have a way to cancel a thread. Therefore, the standard template library and everything we use wouldn't actually use pthread cancel at all. Now, if it's not used, then the diligent linker wouldn't link it. And then this kind of magic here with the attribute weakref would create here a weak reference in this macro. Behind this macro would create a weak reference with a funny name, which is, and the pointer here is set to that weak reference, and that is null pointer. So the net effect of this is, if you write a C++ program, you link with libmusl, you use pthread create, but not pthread cancel, and you don't use this if you just play C++. Then this bloody mutex isn't one. It's nothing. It's not doing anything. Which means that in this rather peculiar situation, it is entirely possible that if two exceptions happen at the same time, approximately at the same time, then one of them can grab an object from the unseen objects list and then got scheduled out for more than, say, 50 milliseconds. Then the other moves on, also grabs the object. One of them goes on first and does a completely proper insertion into this list. And then the other is scheduled again and runs into the problem I have visualized on the slide. And then we have the problem. Nothing happens during runtime, all is fine. Everything works because the data structure can be used to find this guy. However, it doesn't shut down because the code which is run after the main program actually runs into an infinite loop, exactly what I've seen. So here we go. We have understood what's happening. So here's the list of conditions which have to happen such that you run into this problem. You need to be on Linux. You need to not be using glibc, otherwise we would have looked for pthread create, which we do link. You must not be on Android with the Bionic C library. You must statically link the executable. You must not explicitly use pthread cancel. And then it must actually be the first exception which is ever happening in your C++ program. And that must happen in two threads exactly at the same time. Where exactly at the same time means exactly enough such that the high load can lead to the fact that one of them starts this non-critical section now and grabs the unseen object, and then the other grabs it, and then they both continue. So we also need that one of the threads is suspended in at an unlucky time. Right, you would think this never happens. Don't think so. It does happen. That's why we have mutexes, and that's why we should actually use them. Right, whose fault is this? Before I move to that, let me show you what, to this day, I actually do in OrangoDB to solve this problem. Now, I'm not very proud of this, but maybe a bit. If you look at this guy here, when we are on Linux, and this is the main function, and the 0th argument does not happen to be this string, which I assume is never doing, but the compiler doesn't know. In that case, I would call the function f. And the function f would use good old-fashioned C methods to actually create a thread, cancel it, join it, and do something with these empty functions here. So that means our program actually uses pthread cancel, and explicitly, the compiler can't get rid of it because if some stupid person would execute it with this program name, then it had to execute it. And the linker is therefore forced to introduce the pthread cancel function, even if it's in a separate module. And therefore, the weak reference is actually becoming a strong reference, and that null pointer check is not true. And therefore, this place in the libgcc, and indeed all other places, actually use proper protection to access memory structures in a multi-threaded program. So that works. Another fix would have been, and this is one I did first, to make sure that the first ever exception in the program happens at main before any other thread is started. That's also safe. So let me just quickly explain why it's only the first one. I dug a bit into this. I can't say that I understood all the details, but what's actually happening in this kind of code here is that these lists here contain essentially the so-called FDEs. That is something like frame description things. Now, if you have a C++ program, maybe I find some proper C++ stuff here. Let's look at some try. Then whenever you do a try thing, then this would be a frame, but every scope you open, this would also be a frame. And that's needed for unwinding, because literally when an exception is thrown in here, then to unwind and find this catch position, it needs to go stack frame by stack frame, decide where the return address is, where in the code we are, and look up something in these data structures libgcc holds in place for us. So that's a really expensive operation. So trying something is cheap, it's for free in current implementations, but actually throwing an exception and unwinding the stack is extremely expensive. Now, these data structures are not small. There are considerably many things in this list here. I don't understand the details. This list itself is not particularly long, but these has sub-objects and stuff, which has a lot of information. And I think out of fear that this might be expensive, it's not done at process start. Rather, it's actually only executed when the first ever exception happens. When the first ever exception happens, then these objects are transferred from the list of on-scene objects to the list of scene objects. And therefore, it's only the first occurrence of an exception in the C++ program which actually makes the problem. Right. So whose fault is it? In my humble opinion, this whole business is an unholy alliance between multiple things. I think that the authors of libgcc have done a bit of over-optimization for the single-threaded case. Obviously, I'm a multi-threaded developer in the sense that not that my brain is multi-threaded, but in the sense that what I develop is multi-threaded. So therefore, I don't really care for single-threaded optimization. I know that it's probably looking better in benchmarks to do this optimization. Anyway, it's just, yeah, well, that's an opinion, whether it's over-optimization or it's an optimization. Anyway, the other thing is subtle differences between glibc and libmusl. Here, the difference is that the pthread cancel function is actually in a different module in libmusl than pthread create. Then it's using black magic from linking and preprocessor stuff to implement this optimization. And then, of course, what comes into play is the overall complexity of exception handling and everything in C++. Now, alles wird gut. So what did I do to get rid of this? First of all, I did the patch in our code. I've already showed this to you. But then I contacted, I believe, libgcc first, who said, when I said, I'm linking against libmusl and static linking, and I encountered this program, because I also produced a little program which demonstrates the problem. This bug report to GCC, because libgcc is contained in the GCC repository, was promptly turned down and closed because they say, oh, this is a bug in libmusl. So I went over to libmusl, posted to their mailing list, and said, no, and said, the libgcc people say, this is a bug in libmusl. And they immediately said, no, it's not. We are behaving entirely within the framework of what's allowed. Why would we want to put pthread cancel into the same module as pthread create. That's our business, nobody else's. And using weak references in this way to detect whether a program is multi-threaded is a bug anyway. And then actually an argument broke out between the two groups, but fortunately it was relatively quickly resolved, because the main maintainer of libmusl pointed out that the same problem had occurred a few years back in libgfortran and libstandard C++. And therefore it was actually fixed, and finally it is actually fixed in GCC 10. So the bug is fixed. It's decided that it was a bug in libgcc. I don't exactly know how it was fixed, probably along the lines how it was fixed for these other guys as well. But it is fixed once we switch over to GCC 10. Unfortunately, I think the current situation is that these days, months later, GCC 10 is out, the bug is fixed, and I think one of us these days made ArangoDB work with GCC 10, so we can compile with GCC 10 now, but for the production build, I think we still use GCC 8.3 for one version and GCC 9 for a later version and so on. So it will be a few months down the line when I can remove this unholy code with pthread cancel again, if I ever do, because it doesn't hurt. So for me, what are the lessons learned, other than that I learned a lot about exceptions and exception handling, C++ runtime, debugging, and perf tools and everything. Don't over-optimize if it costs unnecessary complexity. C++ runtime and exception handling is complicated by definition and by construction. I learned in this context as well that throwing C++ exceptions can actually be quite expensive. I also learned that C code can be very hard to understand, in particular if there's lots of platform-specific stuff and special cases and preprocessor magic, because just to find out what a certain function is actually doing in your configuration is damned hard. And I also learned that the Linux perf are fantastic and an incredible asset for debugging, because they can essentially monitor very, very specific and deep down and low-level stuff without any kind of performance costs. And it gives you great insights, and I could tell other stories about that. So that's really worth your while looking into this. Obviously, something I already knew, open source makes this possible in the first place. It is only because I could actually look into the C code of libgcc in this case to find out what's going on. I probably would not have been able to do this for any kind of Microsoft compiler or whatever. And I learned that the teams who actually develop these fundamental tools, GCC, libmusl, are very responsive. So I had answers very, very quickly and are very much willing to help when problems arise. Obviously, there can be the odd discussion, but whose fault it is and how to fix things and so on. But it was really quickly resolved once I actually knew what's going on. So this is the conclusion of this talk. I've put here together some resources. Let me just quickly show you before I finish. I have actually written an article about this, so you can read all this with a tiny bit more detail if you want. I've linked the actual bug report to GCC here. And there you can also find the resolution. You can find my sample C program to expose the problem. And here's also the bug report for libmusl. And I think the whole email thread where people directly say this is not our problem. And
Matthias just posted the fix in the chat, so where you can find the fix.
Okay.
It's kind of interesting. The solution is pretty much to exclude libmusl from the optimization.
Okay. I can't access the thread here when I share. So let me quickly.
There was also an earlier question of Stefan. I think it's regarding to if you could use GDB watch instead of.
Ah, yes. In principle, Yes, but imagine the situation. You have you have a continuous integration situation where 10 RongoDB clusters are started all at the same time, or at least with a slight delay after startup. Each of them has 6 processes. Each of them has 40 threads. Now, you don't know in which of these instances the problem actually occurs. Maybe you have a guess that it's happening in a database server, not an agent or whatever, but I didn't know where it is happening. And I did know that it's only happening when I have high load. So I would have to start this and then very quickly type and attach GDB to all of them. I might destroy the problem when I attach GDB because there's a delay, which causes failovers and everything. And obviously, I could hack everything that everything is in RunDB and everything, but it's just very inconvenient. And if you look at the beauty of this here, it's just a single executable and 3 lines you type on the shell, and you have the complete information with the call graph and everything, and insight into local variables and so on. Because after all, if I would have watched this and whenever it attaches, do something, obviously I probably can script GDB, but that's extremely complicated. Whereas with the Linux perf tools, it's pretty easy to pull off.
Do you know how it works internally? I suspect it's a hardware memory access trap.
I think what it does, it instruments the actual executable in memory, as far as
I know. Okay. Yeah. Okay.
And it patches the executable to jump somewhere and then do the stuff it would originally do in this place in another place. And I think that's what it's doing.
Right, because
at least for this
embedded systems, at least embedded systems often do provide hardware support for, well, yeah, detecting memory accesses in hardware. And I suspect something like that in modern, well, desktop processors as well, but I don't know.
Yeah, anyway, I would just like to, before we forget about it, thank Max for the talk. And you can't hear us clapping unless everybody opens their mics and claps, but granted, that's probably happening. So anyway, yeah, it's open to discussion. If anybody wants to ask anything, just go ahead, unmute and ask.
Hi, I have a question. Thanks for the talk. Matthias here. Why do you use libmusl instead of glibc?
Because we want static executables. And you can say -static with glibc, but then some of the network stuff just doesn't work anymore. That's because some of the network stuff, for example, host name resolution, is implemented with loadable modules such that you can actually reconfigure it as sysadmin at runtime. And if you have a completely static executable, then loading dynamic modules just doesn't work on Linux. And therefore, you would lose this functionality. And so therefore, if you have a networked server which needs to do network access, then it's just not an option with glibc. Whereas in libmusl, all these things are implemented as a monolith in the library. And so therefore it works. It's essentially the same workaround the Go language does with its own kind of network stack to work around these problems with glibc. And I have to say that completely static executables are a huge benefit because we have just so much less complexity with the different Linux versions. It's the same executable running on Red Hat, whatever version, Debian, Ubuntu, you name it. And this executable actually happens to work on the Linux subsystem for Windows subsystem for Linux as well. And So therefore, you can take our Debian package, install it not only on every version of Ubuntu and Debian and whatever Debian-derived distribution, but you can also install this on Windows Subsystem for Linux, and the same executable works. And so if a customer tells us, I have this kind of stack trace or I have this kind of core, and we just have to know the released version, and we immediately know where to look, and we don't have to take the right package or whatever. That's a huge benefit. And it allows copy-only installation. So you can download a tar.gz, which you just untar anywhere in the file system, and you can immediately run the executable on any Linux. That's a huge benefit. Well, I should say x86-64.
Okay, thank you.
Just a question back to that. Do they actually actively do DL open in the network code there?
As far as I know, yes. It's this. It has to
Right.
do with this NSS switch.
Yeah.
You might have.
Okay.
You might know. Here, you can in configuration files configure how, for example, host lookup works. And the question as to which code is actually run is a runtime decision. And as far as I know, this is done with modules, in particular for these pluggable authentication modules and stuff. So
All right, thanks.
it's actually I don't know whether it's doing DL open or something special, more special, but it's actually, yeah. And if you actually link on glibc and say static, and you use any of these functions, it spits out a very dire warning saying this is not going to work. And I think it's,
well,
true.
At least
it's not going to work.
Yeah.
Yeah.
At least it's explicit about that.
Yeah.
That's okay then.
The disadvantage, of course, is that our executable works around the NSS switch. Yeah. Because I don't know whether libmusl actually respects these switches. I don't know.
Well, you can't have
I was just
everything.
looking, and it doesn't seem to care for them. And it's really hilarious because I just posted the link to the wiki article for name service switch. This is really animal brain of Unix. And this was only pretty much provided so that you could do the stuff like NIS and LDAP and vice versa. Largely for doing management of some resources like users and groups on Linux, but of course also hosts. And if you look at the example NS that comes with any of your distributions, you will find that there is, for example, like now, yeah, I have, for example, in my Ubuntu files, then DNS, MDNS, and then DNS. So this is where it's why these stuff are loaded at runtime, unfortunately.
Yeah. And to be honest, I don't know whether it's an explicit DL open or whether it's used with a shared library loading. But in any case, it doesn't work with static executables. It's kind of sad because I like glibc and I like static executables, and it's kind of sad that that there's not at least a mode to switch to them.
Did you ever find out which exception actually triggered?
That's a good one.
It was in synchronous shard, and I'm wondering if it was because the network layer was not ready or something. I don't remember.
I don't think so. Let's look at replication synchronize. So this is the nowadays version.
We don't see anything.
Ah, you don't see? Did I stop sharing?
Well, we see you.
We see you, yeah. Anything is
okay,
kind of...
Hang on. Let's see whether anything strikes the eye. Yeah. So let me explain where this is. obviously the distributed database does replication. And when such a cluster starts up, it has to synchronize the different copies of the shards. And that's essentially a background procedure which synchronizes followers with leaders. And I think early in the cluster startup, this just can fail. If, say, the follower is a bit faster than the leader and the leader is not yet up again, it's not yet completely up, then such a synchronized operation basically can fail. It's retried automatically, so it doesn't matter. And
well, and an exception wouldn't be exceptionally expensive at this point.
no, in this code, it doesn't really matter whether we do an exception. And yeah, I think this is it. In the beginning of the cluster, such a synchronization just can fail. If it
Makes sense.
just needs some time to get together. And the APIs we are using here are simply done in a way such that failure is reported as an exception. Like it or don't like it, that's the way it is at this stage.
Well, also it sounds like a really good candidate for a first exception anyway.
Yeah, so I didn't really get to the bottom of what this is, but I think if two different shards would try to synchronize approximately at the same time at the beginning and the leader is not yet there, then it can happen.
Yeah, definitely sounds plausible. Thanks.
No.
Yeah, really interesting talk. Really, yeah, it takes quite a bit. And it's really nice to see that the perf tools actually work that way. I've never looked into using them in that way, but that makes sense.
Yeah, they are incredibly useful in such a lot of instances. And
oh yeah. And I assume you pretty much, sorry, you pretty much didn't get any. So initially I was wondering how much logged volume you would get, but then you were only logging the probe, right? Nothing else.
With this perf probe, I was only logging this particular probe, yeah.
So you would end up after, well, potentially days of runtime with almost zero runtime costs. Just the bit of information that you want, nothing
exactly
else.
Yeah, exactly, yeah. That's the beauty of it.
Yep. And it's entirely separated from your process, so it's entirely external. You don't have to modify anything. That's just beautiful.
Yeah. Since I learned the even newer stuff with the extended Berkeley packet filtering, so that is maybe even better. At the time, I didn't know that, because there you can not only log events, but you can actually script in a separate process what's going to happen with them. And it's equally non-intrusive, because it's also just patching the executable, and you can attach it to other types of events like syscalls or whatever. So for example, you can do something under your control in a relatively nice scripting language exactly when your application calls a certain system call or something like that. So that's also incredibly useful. And in particular, you can, for example, react in different ways when you go in and out and measure the time and stuff like this. So that's even more powerful.
Sounds a bit more involved, but then,
Well,
I agree. It's
not too
powerful.
bad. It's
Okay.
not too bad. If
I know it exists. I haven't really used it yet.
Yeah, so if you find the opportunity that you at some stage need it, give it a go, because it's really interesting.
I might actually.
If you look at this here, well, now I'm sharing. Yeah, this is a BPF trace program, and for this particular rabbit hole, I was interested where the time is actually spent when an HTTP request comes into our server and is handed over from boost ASIO to some other thread and then execute it there and potentially asynchronously handled and then back over the IO thread and so on. So here I had to measure time between handover in different threads. Now, if you look at this here, for example, you set the magic variable nsecs, gives you the nanoseconds since the beginning. And this is variables you can store in the BPF trace process. So here I was setting the start to some variable and others to 0. You can print out stuff in the log. And then, for example, when any of these functions is called, that's a wildcard here, or if this function is called, then it would set this particular variable to the current time. Now, if that is called, it sets this other variable to a certain time. And then once the process does the HTTP com task response written, whatever stuff, then you can access all these variables you have accumulated over time coming from executions and function calls in different threads. And you can take the differences and put out all the timings, how much time was spent there and there and there and there. So this time you, for example, can measure how much time you actually spend on a thread handover from a boost ASIO IO thread to one of your scheduler threads.
Nice.
And that is extremely powerful. And it's, well, this would be very tedious to use the normal perf tools, print out a log of whatever stuff has happened, and then put together which events fit to what and so on. And here you have built-in facilities to compute histograms and everything. So that's extremely valuable. So there is documentation is a bit scarce, but once you dig in there.
Yeah, it definitely sounded interesting. I had a cursory look, but yeah. So far it hasn't come up.
Maybe this is a good thing. Now my Zoom window is gone again. Where is it? I think I now have to unshare to find my chat and chat this address there. Here's another question. Have you considered using, for example, GCC attribute used or tweaking the linker script to keep? No, I haven't considered this. If I can, I stay out of linking. That's basically the answer. This is a black magic I try to stay out of. But yes, it could have been done, but this hack here was more sympathetic for me to actually use it if that's what I need to do.
Could also maybe just throw a dummy exception, catch it, and then move on. Just make sure that the compiler doesn't optimize it away.
Yes, I did this in the first thing. Made sure that it happens when the main is still single-threaded. That actually did the job as well. But then you have to play such a trick like this for the compiler to not optimize it away. Yeah, it sounds interesting now and funny, but I can tell you at the time it wasn't funny. It was interesting all the time, but it wasn't funny.
Yeah, I mean, this is a particularly complex case, but the general direction, I think we all know that there are these kinds of bugs, especially when multi-threading is involved somehow. It's always kind of crazy what sometimes happens.
Yeah.
In fact, during your talk, it was reminding me of a very similar case we had a few weeks ago, where we had a bug which was happening only when the process was shut down, and only, of course, when the system was kind of overloaded. So a colleague used it in a way that we never anticipated. So he was running like 400 different threads. And then he put multiple instances on the same machine of that program. And it was completely bonkers. And yeah, in the end, for us, luckily, it was just looking at the code, staring at it for some minutes, and finally we figured out, okay, yeah, there's a mutex missing. There was also some data structure getting corrupted, basically in a very similar way that you just showed. And my takeaway from all of this is that whenever multi-threading is involved, it gets complicated.
Yeah. Recently, we had another case where actually the Linux kernel had introduced a bug in something related to epoll, where a mutex was missing in the Linux kernel, such that boost Asio's method of waking up a sleeping IO thread would no longer reliably work. That was also kind of nasty. But it's also fixed since.
Any more questions? Yeah, it's a shame you don't hear the standing ovations, as I said, and everybody's home office. But yeah, anyway, thank you, Max.
No problem. It was a
so
pleasure.
A murder mystery turned into an advertisement for perf tools. Yeah, if there's no other questions, I would say, I don't know, we close this. And I wanted to also mention that for the last time it was supposed to be announced, we also created a Slack channel for discussions into the in future subjects. Remember, I said that we would like to also have potentially 1 or 2 lightning talks every time around. Yeah, that would be a good place to constantly keep up with the discussion, write ideas, ask for talks, maybe even if you think that somebody could shed light on some stuff that you might find interesting. Suggest speakers that you've heard, let's say, close by, from whom it wouldn't be a big deal to come to Cologne. I mean, right now you don't have to go anywhere anyway. That would be actually the chance to get Herb Sutter or some of the people that are not as accessible. I guess it's not possible anyway, regardless. Yeah, I'm going to advertise the Slack channel again over the website of the meetup, and yeah, then see you in about 2 months time, and bye bye everybody, I guess.